This video shows another example of an iterated integral from section 14.1. The integral from 0 to pi over 4 of the integral from 0 to cosine theta of 3r squared sine theta dr d theta. You can pause the video now, try this one on your own, and come back and check your work. In this case, the iterated integral uses the differentials of dr and d theta. So our inside integral has a differential dr. We're going to treat r as a variable and theta as a constant. And then when we simplify the inside integral, we'll end up with a single integral with the differential d theta. So we would integrate with respect to theta. Since we're integrating the inside, let's go ahead and write our outside from 0 to pi over 4 of what we get when we simplify this whole thing here. When we integrate the inside, the differential is dr, so we're integrating with respect to r, treating r as a variable and theta as a constant. The antiderivative of 3r squared times this constant is r to the third power times that constant, sine theta. And then we evaluate this inside integral at the bounds where r equals 0 is your lower bound and r equals cosine theta is your upper bound. Again, I like to write the bounds r equals so I remember which one to plug in. After you simplify that, you evaluate the single integral at the differential d theta. Okay, when we plug in the upper bound into r, we end up with the integral r to the third power, replacing r with cosine theta. It's going to be cosine to the third power theta times sine of theta minus what we get when we substitute the lower bound in. When you plug in 0 for r, you get 0. So we get the single integral of cosine cubed theta sine theta. Now this is another one you can practice your u substitution. You can let u equal cosine theta. And if du is equal to cosine theta, if u is equal to cosine theta, then your du needs to be negative sine theta d theta. And we have the sine and theta and the d theta. The only thing we're missing is that negative. So if we make that a negative, we can put a negative out in front. If you want to adjust your bounds of integration so that you can save a step on the substituting back in, your lower bound for theta was theta is equal to 0. So if you plug in 0 in for your lower bound, you get your new lower bound for u is equal to 1. Your upper bound for theta was theta is equal to pi over 4. So when you plug that into your what you use for your u substitution, the cosine of pi over 4 is equal to the square root of 2 over 2. So you can make the adjustments in your bounds of integration when you rewrite this in terms of u. So this is going to be negative the integral from our lower bound of 1 to our upper bound of square root of 2 over 2 of u to the third power du. That's our u substitution. Now we can integrate this by adding 1 to the power. We're going to get negative u to the fourth with a 1/4 out in front, or you can divide by 4. Evaluating the bounds from 1 to square root of 2 over 2. When you evaluate the upper bound, it's going to be negative square root of 2 over 2, that quantity to the fourth power all over 4 minus what you get when you plug in 1. So it's going to be negative 1 to the fourth power over 4. And then when you simplify this, you get 3 over 16. Now you can double check that by evaluating this integral, the single definite integral, with a graphing calculator and confirm that you get the same answer. So in this example and the couple other examples that we did, we just practiced evaluating iterated integrals. Now we'll take a look again of what these bounds of integration mean and how we can use iterated integrals. The area of a plane region can be found with a single definite integral like you used in your Calculus 1 and 2 classes. Now in Calculus 3, we can set up double integrals that will also give us the area of regions. In this case, the area of R can be found with a single definite integral from a to b of g2 of x minus g1 of x dx. So when you're setting up your bounds of integration from a to b, that's your left to your right, and then your lower to your upper, it would be the upper minus the lower. Now we can set this up with a double integral and end up with the same value. So we can set up a double integral where the outside differential is dx, so our x is between a and b, and our y inside integral is from y equals g1 of x to y equals g2 of x. When you're setting up these bounds of integration, I like to use the x bounds from left to right, the y bounds from the bottom to the top of the rectangular region. Now I draw this representative rectangle, and that's going to help you out a lot. It's going to tell you whether the region is vertically simple or horizontally simple. In this case, a vertical rectangle indicates that the region is vertically simple. When you slide this vertical rectangle all the way to the left or all the way to the right of the shaded region, the bottom of that rectangle is this g1 of x, and the top of that rectangle is g2 of x. And you slide it to the left, you get x equals a. Slide it to the right, you get x equals b. So our bounds of integration, if you slide it to the left, is your a to b. Slide it from the left to the right, and then the bottom to the top, that's your inside bounds of integration from your g1 of x to your g2 of x. When you set up this double integral where it's just dy dx, the antiderivative of the differential y is y, and then you'll see that you end up with the same formula when you break it down to a single integral. And this is going to be useful as we extend this and go beyond just finding the area of a plane region. Now again, this representative rectangle helps us determine both the order and the limits of the integration. When you draw a long vertical rectangle, the order of the differential should be that dy, the longest direction is your differential y, and your shortest little width there is your dx. So it's the longest times the shortest in terms of that representative rectangle. And again, the outside being the smallest, that's your bounds for x, and the inside is your bounds for y. The vertical rectangle implies the order, again, dy dx, the inside limits corresponding to the upper and lower bounds of the rectangle. And this type of region is called vertically simple because the outside limits of integration represent the vertical lines x equals a to x equals b. Again, I go from left to right, from bottom to top. Vertically simple region, it's important to sketch a graph of these and determine that representative rectangle. Now some regions are horizontally simple. This is not vertically simple because depending on where you sketch the rectangle, the vertical rectangle does not have the same top and bottom or left and right because of the way the region is depicted. This region is horizontally simple. The horizontal rectangle implies the order dx dy. Going in the x direction, that's your longest dimension of the rectangle, and that little change in the y direction is dy. Now, when you have a region that is horizontally simple, the order of the differentials is dx and dy. So the inside are your bounds for x, and your outside are your bounds for y. And your x goes from the left, x equals h sub 1, to the right, x on the rectangle is h sub 2. The bottom, if you slide that rectangle all the way to the bottom, is y equals c. If you slide it all the way to the top, is y equals d. So that's how you're going to get your bounds of integration. Okay, this just summarizes the previous slides. To find the area of a region in the plane, if R is defined between the region where x is between a and b and y is between g1 of x and g2 of x, then the area of the region is set up as a double integral. A is equal to the integral from a to b of g1 of x to g2 of x of dy dx. That's our vertically simple region. If it's horizontally simple and y is between c and d and x is between h1 of y and h2 of y, then the area of that region can be set up with a double integral from c to d of the integral of h1 of y to h2 of y times dx dy. Again, the order of the differentials does make a big difference on how you determine your bounds of integration and how you evaluate the iterated integral.